Identify weak and strong acids as well as weak and strong bases. Identify the Lowry-Bronsted acids and bases. Identify conjugate acid-base pairs. You should also be able to calculate unknown concentrations. During this presentation, we will focus on the following: strong and weak acids, strong and weak bases, concentrated solutions, acid-base theories, acid-base pairs, as well as neutralization. We begin by looking at acids, the properties thereof. Acids have a sour taste, and lemon, you might remember, is an example of an acidic substance because it has a very sour taste. They can be neutralized by bases. Acids in aqueous medium conduct electricity. They are what we call electrolytes. Also, acids, when you put them in water, they ionize to form the H+ ion. We'll talk more about this as we continue. They have a pH less than 7. Again, we'll explain the pH scale later. Common examples of acids include sulfuric acid, which is H2SO4, nitric acid, which is HNO3, and hydrochloric acid, which is HCl. The acids that are present in animal or plant matter are called organic acids. An example thereof is citric acid, which is found in things like orange and lemon, and acetic acid, which is commonly known as vinegar. Next, we look at the properties of bases. A base can neutralize an acid. A base that is dissolved in water, is called an alkali. Alkalis are bitter to taste. They feel soapy to the skin. They can conduct electricity also when dissolved in water. Alkalis have got a pH greater than 7. They produce what we call the hydroxide ion, the OH- ion, when they are in solution. Also, examples that we commonly know of alkalis are sodium hydroxide, which is NaOH, potassium hydroxide, and also ammonia. In the previous slides, we mentioned acids as having a pH less than 7 and bases pH greater than 7. Let's look at what pH is. pH is a number indicating the degree of acidity or basicity of a solution. And we have what we call the pH scale, which ranges from 0 to 14. And here we have our pH scale, starts at 0 all the way up to 14. And substances that have got a pH value between 0 and less than 7, those substances are referred to as acidic. Substances which have a pH value of 7, they are referred to as neutral. And substances with a pH value greater than 7, between greater than 7 and 14, those substances are called alkaline. Another means of determining whether a substance is acidic or basic is making use of an indicator. An indicator is a substance that changes color depending on the pH of the solution. So it gives a certain color when the substance is acidic. It gives a certain color when the substance is alkaline. There is a wide range of indicators, but we'll look at a few indicators, some common indicators, and their colors and the ranges in which the color change happens. And here's the list. We have what we call thymol blue, bromothymol blue, methyl orange, methyl red, and phenolphthalein. Thymol blue, the color in an acid is red and it is yellow in a base, and the pH range for its color change is between 1.2 and 2.8. Bromothymol blue, which is very common, is yellow in an acid, blue in a base, and that's the pH range. Methyl orange, orange in an acid, yellow in a base, and there you have the pH range. Methyl red is red in an acid, yellow in a base, and the pH range for its color change is between 4.2 and 6.3. Phenolphthalein is colorless in an acid, pink in a base, and the color changes between 8.3 and a pH of 10. Our next concept is acid and base strength, or acid and alkali strength. By definition, a strong acid or a strong alkali is one that ionizes completely in water. Strong alkalis contain a very high concentration of hydroxide ions, OH- ions, and strong acids contain a very high concentration of hydrogen ions, the H+ ions. A strong acid, if you look at the pH scale, it's got a very low pH, it's got a pH close to 0, and a strong base has got a higher pH, its pH is very close to 14. What about weak acids and weak alkalis? Well, a weak acid or a weak alkali is the one that does not ionize completely in water. We often say they ionize only partially in water. Weak acids contain a low concentration of H+ ions, and weak alkalis also contain a low concentration of hydroxide ions, OH- ions. In terms of the pH scale, a weak acid, although it's got a pH less than 7, but that pH value is close to 7, so you would have a value of about 6.5. It's an acid, but a weak acid. A weak base has got also a lower pH, although the value is above 7 to indicate that it's a base, but it will still be close to 7. So for example, a pH value of 8 indicates a weak base. When referring to acids and bases, we sometimes talk about dilute and concentrated acids or dilute and concentrated bases. Let's explain this concept. Concentration, in this case, is a measure of the amount of acid or alkali there is in a solution in relation to the amount of water that is present. For example, a concentrated acid or a concentrated alkali has got very little or no water in it, and a dilute acid or a dilute alkali has got a larger amount of water that is in it. There are two models that are used to explain the behavior of acids and bases. The one model is called the Arrhenius model, and the other one is the Lowry-Bronsted model. Let's start by looking at the Arrhenius model. According to this model, an acid is a substance that ionizes in water to produce hydrogen ions, H+ ions. Here's an example. If we take nitric acid, when you put it in water, it ionizes to form the H+ ions and of course the nitrate ion. So this would be an acid by using the Arrhenius model. Also, according to this model, a base is a substance that ionizes in water to form the OH- ion, the hydroxide ion. Example is sodium hydroxide, which when dissolved in water forms the OH- ion plus of course the sodium plus ion. So this is the Arrhenius model. The second model, the Lowry-Bronsted model, is often referred to as the proton transfer model. According to the Lowry-Bronsted model, an acid is a proton donor and a base is a proton acceptor. And by protons in this case we mean the H+ ion. Basically the hydrogen plus ion is the proton that we are referring to. Let's have a look at this example. If you take hydrochloric acid and you put it in water. Now, what happens here is that the HCl donates the H+ ion to the H2O, forming the H3O+ ion. And the H3O+ ion is referred to as the oxonium or the hydronium ion. So, if the hydrochloric acid or the HCl donates the proton, it is therefore the proton donor, which means it is the acid according to this model. And the water in this case accepts the proton, so it's the proton acceptor, and according to this model, the water acts as a base. When looking at proton transfer, there's a special group of substances that are referred to as ampholites. These are substances that can react both as an acid, also as a base, and when we refer to them, we say they are amphiprotic, or we call them ampholites. A common example is water. Here we look at water acting as an acid. In other words, water donating a proton, dissociating in water to form H+ and OH-. Here in this case water is an acid. But also water can act as a base. And here's the example where water receives a proton to form the H3O plus ion. So it can act as an acid as well as a base, and so we refer to it as an ampholyte. There are other examples of ampholyte. The HSO4 minus ion. When you look at this ion, it can receive a proton, making it a base, but it's got an H plus ion here, which means it can also donate a proton, making it an acid. The HCO3 minus ion is also another example of an ampholyte. Still on proton transfer, we have what we call mono or protolytic reactions. A protolytic reaction is any reaction in which a proton transfer takes place. Acids that donate one proton are referred to as monoprotic acids. An example would be hydrochloric acids, only got one proton to donate, so it's called monoprotic. Acids that can donate more than one proton, in other words multiple protons, are referred to as polyprotic. Another example of a polyprotic, in this case specifically diprotic, is sulfuric acid because it's got two protons to donate if you look at its formula. And that is how it donates its two protons. It can donate the first one and we are left with HSO4 minus, but it can also donate that proton, leaving it with SO4 2 minus, so it's diprotic. Another example is phosphoric acid, which is triprotic because it's got three protons to donate. So it can donate one and we are left with H2PO4 minus, can donate another one and we have HPO4 2 minus. It can donate a third one and we are left with PO4 3 minus. So the sulfuric and the phosphoric acid are referred to as polyprotic, but specifically the sulfuric is diprotic and the phosphoric is triprotic. Acids and bases can react with each other. They can also react with other substances. But a common reaction that often takes place between an acid and a base is referred to as a neutralization reaction. Now, if we consider an aqueous acid-base reaction where we react an acid and a base, the end product will be salt and water. Now, a salt is an ionic compound which contains a cation and an anion, but it contains a cation other than the H plus ion, and it contains an anion other than the OH minus ion. That's what a salt is. Now, if, for example, we take equal molar amounts of a strong acid and a strong base, at the end, only a salt and no acid or base will be left. Also, the final pH of this solution, or the final pH of the salt, will be equal to 7 when we have a strong acid and a strong base. At the end point, we have what we call the point of neutralization. So at the end point of this reaction, normally it's the point where the indicator changes color, we have that point referred to as the point of neutralization. An example of a neutralization reaction is the reaction between hydrogen chloride gas and ammonia gas. If you take a glass tube and take a piece of cotton wool and soak it in ammonia, and take another piece of cotton wool and soak it in hydrochloric acid, and then put these two at the edges of the glass tube as shown, and then close the glass tube on both sides, what you will observe is the diffusion of both the ammonia and the hydrogen chloride gas, but the ammonia diffuses faster than the hydrogen chloride, but at the point where they meet, there is a white cloud or white fumes forming, and those white fumes is ammonium chloride crystals. And the reaction that takes place is hydrogen chloride plus ammonia forming ammonium chloride, and the ammonium chloride is a white solid, hence the white cloud forming over there. The product forms off center, the ammonium chloride forms off the center due to the different dispersion rates of the hydrogen chloride and the ammonia. So basically the ammonia diffuses faster because it's lighter as a substance than the hydrogen chloride, so the reaction takes place closest to the hydrogen chloride because it is heavier than the ammonia. Another example of a neutralization reaction is the reaction between hydrochloric acid and sodium hydroxide. And that's the reaction. When these two react, they form sodium chloride and water. And sodium chloride, the salt that is formed, is commonly known as table salt. The acid, hydrochloric acid, and the base, sodium hydroxide, are both strong electrolytes. In other words, we've got a strong acid and a strong base, and so they ionize completely in water, as shown in this reaction here. The hydrochloric acid ionizes to form the H+ ion and the chloride minus ion, and the sodium hydroxide ionizes to form the sodium plus ion and the hydroxide minus ions. And when these two react, they form water and the salt, but also the salt ionizes to form the chloride minus ion and the sodium plus ion. So what actually happens is that the chloride minus ions cancel each other out, and the sodium plus ions cancel each other out. So the actual reaction that takes place is really between the H+ ion and the hydroxide minus ion to form water. In other words, the sodium plus ions and the chloride minus ions are basically what we call spectator ions. Next, we look at how acids react with various substances, starting by looking at the reaction between an acid and a metal oxide. In general, when an acid reacts with a metal oxide, we form salts and water. And the example that we are going to look at is the reaction between sulfuric acid and copper oxide. And that's our reaction equation. When sulfuric acid reacts with copper oxide, we form the salt, copper sulfate, and water. And if that's our beaker in which the reaction is taking place, we have the acid, which is colorless, and then we add the copper oxide or the metal oxide. In this case, it's black. But when the reaction continues, we notice that when the copper oxide reacts with the sulfuric acid, we form copper sulfate, which is blue in color. And when the copper sulfate dissolves in water, the color of the solution becomes blue. And so this side, or the product end, is blue. And the reason for the blue color is due to the presence of the copper 2+ ions, which basically form when the copper sulfate dissolves in the water. The second reaction of an acid that we look at is when an acid reacts with a metal carbonate. In general, when an acid reacts with a carbonate, we form salt, water, and carbon dioxide gas. An example is when we react sulfuric acid with magnesium carbonate. What we actually form is magnesium sulfate, the salt, water, and carbon dioxide gas. And that's the reaction equation. Sulfuric acid reacting with magnesium carbonate to form magnesium sulfate salt, water, and carbon dioxide. So basically in this reaction, a large carbon dioxide bubbles are formed. And how do we know it's carbon dioxide? We take the gas that is being formed and bubble it through clear lime water. And if the clear lime water turns milky, then we know that the gas that we have formed is carbon dioxide. Next, acids plus metals. Again, a general equation. An acid plus a metal reacts to form salt and hydrogen gas. And this reaction is often used in the labs to prepare hydrogen gas for use in other reactions. An example would be a reaction between hydrochloric acid and zinc metal, and the salt that is formed is zinc chloride, and of course we form hydrogen gas. Now, these three reactions that we've just looked at, acid plus metal oxide, acid plus carbonate, and acid plus metal, please note that they are not acid-base reactions, but they are actually redox reactions. But we'll talk about redox reactions in another lesson. The type of salt formed in these reactions depends on the acid used. If the acid is hydrochloric acid, the salt that is formed is a chloride. For example, when we reacted hydrochloric acid with the zinc, we formed zinc chloride. If the acid is nitric acid, the salt formed is a nitrate. For example, if we react nitric acid with potassium hydroxide, we form potassium nitrate. If the acid that is reacting is sulfuric acid, the salt formed is a sulfate. For example, if we react sulfuric acid with copper oxide, we form copper sulfate. The next key concept in this lesson is the concept of acid-base pairs. Reactants and products in an acid-base reaction can be paired into what we call conjugate acid-base pairs. And basically, an acid and a base in this pair, in the conjugate acid-base pair, they differ by one proton. If we consider this reaction where hydrochloric acid is in water forming the chloride minus and the H3O plus ion, remember that the HCl, because it donates a proton, it's the acid, and we are left behind with the Cl minus ion, and so that becomes the base. And so the HCl and the Cl minus ion are the conjugate acid-base pair. Conversely, the water and the H3O plus ion are also another conjugate acid-base pair. The water is the base because it receives the proton, forming the H3O plus ion, which makes this one the acid. So the acid in the conjugate pair is the one that is rich in protons. If you look at how these conjugate acid-base pairs form, basically an acid donates a proton to form its conjugate base, and a base accepts a proton to form its conjugate acid. To explain this, let's use this example, ammonia reacting with water. Basically, the ammonia accepts a proton to form its conjugate acid, and the water donates a proton to form its conjugate base, which is the OH minus ion. In summary, the ammonia is the base, and the NH4 plus ion is its conjugate acid, and the water is the acid, and the OH minus ion is its conjugate base. Here's a challenge to test your understanding. Ammonia dissolves in water as follows, as shown in this reaction here. 1.1. Does the ammonia in this reaction act as a base or as an acid? 1.2. Explain your answer to 1.1. And 1.3. Write down the conjugate acid-base pairs for the above reaction. Here's the proposed solution. First of all, there's our equation that we are dealing with. The first question was asking whether ammonia is an acid or a base. Well, the ammonia here is a base. The reason for that is because the ammonia accepts a proton to form the NH4 plus ion. And then we were to give the acid-base pairs. Well, the ammonia is the base and the NH4 plus ion is its conjugate acid. The water acts as the acid and the OH minus ion is its conjugate base. Neutralization reactions can be used to determine the unknown concentration of an acid or a base. And to do that, we must remember that at the end point of an acid-base reaction, the number of moles of the H plus ions is equal to the number of moles of the hydroxide ions. But we also know from our previous lessons that number of moles can be calculated by multiplying the concentration by the volume. And therefore, if we divide the number of moles of the acid by the number of moles of the base, we come up with this equation. Na over Nb equals to CaVa divided by CbVb, where N is obviously the number of moles of the acid or the base, and C the concentration of the acid or the base in mole per cubic decimeters, and V the volume of the acid or the base in cubic decimeters. To calculate the unknown concentration, these are the steps you must follow. Step 1, you must write the balanced equation for the reaction. Step 2, from the balanced equation, determine the molar ratio, in other words, the ratio of the number of moles of the acid versus that of the base from the reactants. Step 3, substitute that information into this equation. And then the last step is then to calculate the unknown quantity. Here's a second challenge for you, this one dealing with acid-base calculations. Here's the question. A student is provided with 20 cubic centimeters of concentrated hydrochloric acid. The student then dilutes this solution by pouring the 20 cubic centimeters of acid into 180 cubic centimeters of distilled water. The 200 cubic centimeters of solution is now neutralized by 25 cubic centimeters of sodium carbonate, which has got a concentration of 0.44 mole per cubic decimeter. Now the question, calculate the concentration of hydrochloric acid in the undiluted acid solution. Now my advice to you is to pause the DVD at this point, do this calculation on your own, and then view the answers later. Here is the solution to the previous question. First of all, we must write down what you are given. The volume of the acid is 20 plus 180, so the volume of the acid is 200 cubic centimeters. The volume of the base is 25 cubic centimeters. The concentration of the base, 0.44 mole per cubic decimeter. We are then asked to calculate the concentration of the undiluted acid. Step 1, remember, was to have the balanced equation, and here's the balanced equation. 2 moles of hydrochloric acid react with 1 mole of sodium carbonate to form 2 moles of sodium chloride plus 1 mole of carbon dioxide and another 1 mole of water. Step 2, from the balanced equation, we must then give the molar ratio. Well, these are the substances that we are dealing with, the hydrochloric acid and the sodium carbonate, the acid and the base. And that is the molar ratio. The number of moles of the acid is 2 and the number of moles of the base is 1. We basically take the coefficient in front of the substance. And the last step is to then substitute into the formula. Remember, there's our formula, Na over Nb equals to CaVa divided by CbVb. If we substitute 2 moles of the acid divided by 1 mole of the base, we do not have the concentration of the acid. We've got the volume of the acid, we've got the concentration of the base, we've got the volume of the base. And we make Ca, concentration of the acid, the subject of the formula. The final answer becomes 0.11 mole per cubic decimeter. This is the concentration of the diluted acid. However, the question asks us to calculate the concentration of the undiluted acid. To do that, to calculate the concentration of the undiluted acid, we use the formula C1V1 equals to C2V2. This is because the number of moles of the acid is the same. And so we have C1, which is the concentration that we want, times the volume of the undiluted acid equals to the concentration of the diluted acid times the total volume, which is 200. So in the end, the concentration of the undiluted acid is 1.1 mole per cubic decimeter. We have now come to the end of this lesson. Please note that for additional challenges, you can refer to the grade 11 copy of the Study and Master, and on page 261 you'll find activity 6, and on page 262 to 263 you'll find activity 7, both of which are dealing with questions on acids and bases. Now you must remember that for you to benefit maximally from these DVDs, you must watch each lesson more than once and also do the worksheets that accompany each DVD.